This video focuses on how to find equations that describe the null geodesics followed by massless particles, such as photons, in the equatorial plane of a Kerr black hole. The final equation sought here is of the form phi equals phi of r, which is then substituted with 1 on u, which enables the use of numerical integration to plot the null geodesics followed by these particles. Alright, so we want to describe the motion of massless particles such as photons, gravitons, and perhaps some neutrinos in the equatorial plane of a rotating uncharged black hole, so the Kerr black hole. Now these particles travel along geodesics described by the coordinates x mu. We've covered that in previous videos. We can imagine this we can imagine photons traveling in the equatorial plane of this black hole. We can parameterize the world line of the particles in the form x mu as u of mu lambda, all been covered in previous videos, so I won't repeat that. Now, the form momentum vector of the photon is tangent towards the world line. P is x dot mu e mu. Now, we parameterize the form momentum of the photon in terms of the derivatives of its coordinates, and we've scaled these coordinates to give us, so that when we substitute these coordinates in, we get the total components of the form momentum of the photon in this geometry. So we are free to rescale these coordinates until they produce the values that we need for the form momentum of a photon. I've covered that in the last couple of previous videos. And the point here too is, as in the previous videos, that at every point in this world line of this photon, the form momentum vector is tangent to the world line of the particle at every point on it. And that's visually depicted here. Obviously I can't show the time axis, so you'll have to imagine that. Alright, now there are two symmetries in the Kerr geometry that can help us establish relations that describe the motion of these particles. If you remember the Kerr metric, which I've not explicitly stated here, but many times in the previous videos, there are two coordinates which are not explicitly represented, the time one and the azimuthal angular coordinate. They don't explicitly appear in the metric because the geometry is independent of those two. And we can express that independence of the geometry with killing vectors in these directions. So we take a killing vector in the time direction, a killing vector in the phi azimuthal direction, okay, which is perpendicular to phi's points in the direction perpendicular to the rotation axis of the black hole. So in the time direction we have this one, C 0, 0, 0. Remember, just scaling by C, because with my space-time interval on this channel, I use CT instead of just T. So it's scaled by a factor of C, which makes that component, gives it units of distance. So we get ET, the basis vector here is just C, and then all the other components are 0. And then if we take the total derivative, d to lambda, of this killing vector dotted, or the inner product with the form momentum vector, it just picks out the first component. All the others are 0 because the killing vector is 0 and those other components. So d lambda gives us GTT, the metric term, KT, PT. Well, KT is 1, put that in there. Oh, sorry, not 1, it's C. GTT, C, we'll take the constant out front here. And then the metric term GTT will lower the index, lower the contravariant index on this form momentum vector and lower it down to give it to the one form, PT, covariant index PT. That's equal to 0. And so the first integral tells us that C times PT is minus E. We can also, as we found in the previous videos, express this in terms of its metric and components, so that the PT component is C times GTT CT dot times C plus C GT phi dot is minus E. Okay, so expressing in terms of the coordinates and the metric terms, we write this out. Both of these have a T component in them, that's why they appear. None of the other metric terms have a T component in them, or the T index here. They don't. T does not explicitly appear in the metric. Sorry, I didn't mean to cause confusion there. But when we list all the components of the metric, the T components, or components involving T, must explicitly appear. So GTT, GT phi, okay, is minus E. Now, in the azimuthal direction, we have K phi, E phi, 0, 0, 0, 1. Okay, so again, the derivative here with respect to the affine parameter lambda, K dot P, gives us all of this. Well, K phi is 1. So G phi phi lowers the index on that contravariant term component, drops it down there. P phi is equal to 0. So straight away, our first integral tells us that P phi is equal to constant. So that the form momentum in the component of form momentum in the phi direction is equal to a constant. And from previous video, we found this equation here as well. All right, so we can write P phi out in terms of all its coordinates, gt dot and phi dot. Okay, so that was all, by the way, in Boyle-Lindquist coordinates. Now, in the previous video, back in Kerr geodesics 13, we found the equation of motion for massless particles to be r dot squared. It's all of this. Okay, rewriting that r dot plus this bit here is equal to this these constants here. We get r dot squared plus an effective potential term right here. We explored all that in previous videos. That's equal to the total energy of the orbit, E. And so we know that c squared epsilon squared is equal to E, the energy of the orbit, where epsilon is the energy parameter. Okay, we've covered that in previous videos. And so c times epsilon is the square root of E. Now that's important, the square root of E, because that tells us that we can't have values of E less than 0. It's simply not possible. Well, it doesn't mathematically make sense. It's not physically real to have square root negative something, a negative quantity. But if you remember with the particles with mass, massive particles, E could take on negative values. And that allowed those bound orbits, those beautifully bound orbits that precessed. Well, that does not happen here with the photons. They cannot take these negative values here. So we're still going to have bound orbits of a sort. For instance, we're going to have plunge orbits where it spirals into the black hole. And we're also going to have not just plunge orbits, but we'll have other orbits, such as parabolic ones, deflection orbits, scattering orbits. Okay, so they'll be possible, but we just won't get those beautifully bound ones that precess and so on, because E can't take negative values. But a range of other orbits are allowed, and we'll explore those in the next video after this. So we have here from r dot, from here, r dot dr, which is dr d lambda, is the square root of E minus V effective. So that's just E minus V effective is r dot squared, and the square root of that is E minus Vf. So that's r dot. Now, from previous videos, I was explaining we had P phi as this. And what we're going to do now is we're going to use this equation and this other one here, and we'll be able to describe its motion and produce something which we can later on plot, numerically integrate, then plot and produce a parametric plot of the motion of the particle. Okay, so what we'll do then is from this second equation here, we're going to rearrange, we're going to solve for CT dot and by itself. So with GTT, CT dot is minus E on C minus GT phi dot. And we did all of this with the particle with mass, for the massive particle case. So it's the same sort of thing, but the equation is a bit different here because we're dealing with the massless case. Multiplying through by the inverse metric term gives us minus GTT, E on C minus all of this. Okay. And what we'll do is now take all of this and we'll substitute that back into our first equation up here to eliminate the CT dot term. So put that in there. Here we go, G phi t, and then all of that goes in from this, plus G phi phi dot, and expanding that out to remove the parentheses, we have this. Okay, and just like we did with the massive case, rewriting the last line again, this is what we had. Now we'll substitute in G phi t is here. The inverse metric term GTT is 1 on delta times all of this. Then over here we have G phi t and GT phi, they're the same, the symmetry in the metric means those two things are the same. So multiplying them together is the square of one of them, this object here, times the inverse metric term here, all this, plus that last bit, which I won't expand just yet. We'll do that later on near the end. We don't need to do it now. Let's have a look at these first two terms. We might be able to simplify something here or even make an approximation ultimately. So what we're looking here in the first term here, we have the G phi t term out front. Then we have 1 on delta. Now 1 on delta, as in the previous videos, gave us this. I won't go through that again. Gives us this. And then we have this term here, okay? And the same over here, G phi t squared. Then 1 on delta here again, times this term again, plus the n term. All right, next thing we'd like to do now is let's get a common denominator for this and also for this. So we write that down here. common denominator c squared r. Same thing down here, c squared r, common denominator. Okay, and we'll expand this out. Okay, this r will go in here, gives r cubed, r times r to give us the r squared, r and r over here, over this. Okay, now same thing down here. Okay, expanding that out because we get, we get the square of all this, so that goes here. Numerator 2gmac all squared right here, and then over the bottom here, c to the 4 r squared. Multiply that through here. We get all this plus all this. Okay, so I hope everything's clear there. The last term here I won't expand just yet. So we're looking for common denominators, and then what we'll do, we'll start combining a few things. So we'll take this numerator here over the top of this denominator, this numerator here over the top of this denominator here. Next slide over. Okay, here we go, and we get this over that times e on c squared r plus this times all of this, so that over that. This bit here. Now, if you notice here, the highest term here is r cubed, highest ordered term, r cubed over an r cubed, r over r, and so on. Over here, we get r cubed over r cubed, same thing again. Okay, and what we can do is, as an approximation, we'll set those equal to about 1. I did do in a previous video, I had a look at those. If you plot these two things, you find it's roughly a constant line straight out. So we can cancel, we'll cancel it down to 1. So that's our first approximation, we'll reduce that to 1. All right, and then so we get 2gm over c squared e on r plus 2gm squared phi dot over c squared r squared, okay, times this n term here. And next line down, what we'll do is I'll write out this g phi phi, which is this. If you have a look here, you've got 1 over r here, you've got 1 over r squared here, but here you've got an r squared dependency and then a small term added on the 1 over r term here. Plus you've got an a squared term here. Okay, now what that means is then that this last term here somewhat dwarfs these first two terms. It's vastly larger because of the r squared factor and then plus this other constant a squared here. Altogether, it's larger than these 1 over r and 1 over r squared terms. Okay, so what we can then do with that is, I'll go back to calling that g phi phi times phi dot here, but then what we do is we'll just say as an approximation, okay, we can say that this is the dominant term by far, so we'll reduce this to g phi 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 dot is approximately equal to h, okay, because these are small in comparison with g phi phi. So these terms here individually are small in comparison to this. Even together, they're small in comparison to this by far because of the r squared. Okay, so g phi phi times phi dot is approximately h. Rearrange that, phi dot is approximately h on g phi phi. Our next step then, so we have phi dot is d phi d lambda is approximately h on g phi phi. For ingoing geodesics, we should point out r dot should be the negative of this. A plus here means an outgoing geodesic, r dot increasing, r dot negative means ingoing geodesic. d phi dr is phi dot and r dot is approximately h on that times 1 on this. Okay, d phi dr is phi dot, that one over r dot, okay, so that times 1 over r dot, so 1 over that. Okay, I should have put a minus in there. I've left that out. My apologies. There should be a minus in there. Okay, now next step is we're going to make the following substitution. R is 1 on u. It's easy to work with and integrate with to have the u upstairs and an r down below. And we get dr du is minus 1 on u squared. So v effective in terms of u and not as a function of u and not of r is this, as we've seen from previous videos. G phi phi, again from a previous video, we see it takes this form here. The r's are replaced by the u. 1 over u, sorry. Next bit, we see d phi du is d phi dr times dr du, minus 1 on u squared, that's dr du, times now this minus here appeared because remember this was 1 over square root of e minus v, that was negative, so I've just put the minus up here, it's more visible. So these negative signs cancel. Left with h over this times 1 over that. Okay, so phi to u is approximately, to a good approximation, is this. All right, what we can now do is numerically integrate this to find the total change in angle phi between any 2 points in its orbit. So how much does phi change by? What's the total change in phi over this orbit if we pick any 2 points on the orbit? So that'll be the integral from u1, our first point, 1 over r1, to u2, 1 over r2, and we'll integrate that in terms of u. And we'll use numerical integration for that. All right, and then the next step after that is to plot this parametrically in the two-dimensional equatorial plane in the form of x is square root of that times cos of phi plus y equals square root of that times sine phi. Remember, oblate's spheroidal coordinates apply here because there's a bit of flattening in the equatorial plane in the direction perpendicular to the rotation axis. There's this dilation away from the rotation axis, especially more pronounced about the equatorial plane than elsewhere. That's where the phi direction symmetry differs. The phi coordinate differs from the polar coordinate because the polar coordinate changes the geometry, whereas for constant, you have for different planes, you have constant phi component of angular momentum. Now, there exists a good program for carrying out this integration using a Mathematica program that can be found on the website that accompanies James B. Hartle's textbook called Gravity: An Introduction to Einstein's General Relativity, an excellent book. Really recommend that. There are many very good books around and many very good resources on the internet as well. So just a plug for all of them. Other versions can also be found on the web. You'll need to modify it to deal with the Kerr geometry because it was written for the Schwarzschild case, and I'll show you that shortly. Let's go there now. And okay, so here we are, equatorial orbits in the Kerr geometry, and we'll make some adjustments. We're going to work in units m equals 1, g equals 1, c equals 1. Substitution u as 1 and r is used. Right, now you need to set the angular momentum, give it a value, and the energy parameter here is c squared epsilon squared. The starting radius, the label RST, and the number of orbits to compute if the orbit is bound is an orbit, and we'll settle those later on. Okay, so we'll do that. Play around with this, you can read the instructions and so on. I'm just going to give you a brief look. So we come down here, we're going to set, we're going to put our V effective in here in terms of u, the one that you saw earlier, put that in there. Set the angular momentum, you can try different values, play around with it, get all sorts of shapes. It plots the effective potential. Then you can set the energy parameter here, and I've set it just slightly above the maximum of the V effective. Maximum V effective is 0.264. I've set the energy here at 0.265, just above, because I wanted to show you a plunge orbit. I love looking at those plunge orbits. It's all good fun playing around with it and so on. What else was there? Okay, keep going down. Sensitivity I've set to 1 in 10 to the minus 10. Pretty ambitious there. And there's reason for that. I won't go into that. Anyway, there's some information about the orbit. It carries out tests for you. And we're going to see tests for plunge orbits here. And look at this. Here's our expression again from earlier. Remember the H, which in this program is just called L. And del phi is the total angle swept out. Endpoints. Remember parametrically plotting it. Oblate spheroidal coordinates, so we had to plot x and y. And when we do that, I come down here. Yes, that's what the plot looks like, but I've added the disk to represent the Kerr black hole. Set that. The blue line represents the outer event horizon. The actual stationary limit surface goes up here to the value of 2. That's the stationary limit surface. At that point and inwards, a particle, whether it's a photon or a massive particle, must rotate with the black hole itself. So you can play around this program and try giving the photon a negative value for its angular momentum. Here's what a plunge orbit looks like. Love playing with those. And there's other sorts of others. And what I'll do in the next video is I'm going to make that a focus of those videos, just showing some different types of orbits by playing around with them. But also what I'm thinking of doing in the next video is I'll put in a disk here to show you, should be about here, to show you the inner event horizon, and I'll just change the limits of integration so it does go all the way in. So I should be able to do that. At the moment, I'm just showing you the outer event horizon and not even the stationary limit surface, which would be here at about 2. Okay, that will be it, I think. So I'll close that. and we're finished there.